What problem does the proposed method, information-intensive in-2 training, aim to solve in the context of long-context large language models, LLMs?
The proposed method, information-intensive in-2 training, aims to solve the lost-in-the-middle challenge in the context of long-context large language models, LLMs. This challenge refers to the difficulty these models face in effectively utilizing all the information provided in the long context, where they tend to overlook the information in the middle while comprehending the beginning and end of the context. In-2 training addresses this issue by explicitly teaching the model that crucial information can be intensively present throughout the entire context, not just at the beginning and end. It aims to overcome the unintentional bias hidden in the general training data, which may suggest that important information is always located at the extremities of the context. By utilizing a synthesized long-context question-answer dataset and training the model to be aware of fine-grained information and integrate reasoning across different segments, In2 training significantly enhances the long-context information awareness of LLMs, as demonstrated by the probing results and real-world task performance improvements presented in the study.
How does the proposed In2 training method work, and what key steps are involved in the training process?
The proposed In2 training method works by explicitly teaching the model to utilize crucial information present throughout the long context, not just at the beginning and end. The key steps involved in the training process include data construction and training. Firstly, a long context question-answer training dataset is constructed, where the answer to a question requires information from randomly placed short segments within the long context. Two types of question-answer pairs are generated, one focusing on fine-grained information awareness within a single segment, and the other on integrating and reasoning information from multiple segments. The dataset is balanced in length from 4K to 32K tokens to prevent bias. Additionally, to avoid forgetting short context capabilities, some question-answer pairs are retained in their original short context form. The dataset consists of long context data for fine-grained information awareness, integration and reasoning of information, short context question-answer data, and general instruction tuning data. The training process involves fine-tuning the model using the constructed data in an instruction tuning paradigm, where long contexts and questions serve as instructions, and the loss on the answer parts updates the model. The training is conducted with specific hyperparameters, including a global batch size of 128, one epoch training with around 14K steps, and a cosine learning rate decay strategy. The training is performed on multiple GPUs over 300 GPU days.
What are the theoretical or practical benefits of using In2 training for long context LLMs compared to traditional training methods?
The theoretical and practical benefits of using In2 training for long context large language models, LLMs, compared to traditional training methods are significant. The key advantage lies in addressing the lost-in-the-middle challenge faced by long context LLMs. In2 training explicitly teaches the model to utilize information intensively throughout the entire context, not just at the beginning and end, thereby overcoming the bias towards the edges of the context present in traditional training methods. This leads to improved long context information awareness and utilization, as demonstrated by the probing results showing that In2 training significantly mitigates the lost-in-the-middle problem for the backbone model. Furthermore, the synthesized long context data used in In2 training effectively generalizes to real-world scenarios, resulting in significant performance improvements on various real-world long context tasks. This indicates that the benefits of In2 training extend beyond synthetic data and can be applied practically to enhance the model's performance in real-world applications. Additionally, In2 training maintains the performance on short context tasks, ensuring that the model's capabilities in handling shorter contexts are not compromised during training, which is crucial for maintaining overall model versatility and applicability. Overall, the In2 training method offers a data-driven solution to enhance long context LLM's ability to fully utilize information throughout the context, leading to improved performance on both probing tasks and real-world scenarios. This approach not only addresses the specific challenges faced by long-context LLMs, but also demonstrates the potential for open-source models like Film 7b to achieve comparable or even superior performance compared to proprietary LLMs like GPT-4 Turbo, showcasing the effectiveness and practical benefits of using IN2 training for training long-context LLMs.
How was the effectiveness of the IN2 training method validated or tested, specifically in terms of probing tasks and real-world long-context tasks?
The effectiveness of the IN2 training method was validated and tested through probing tasks and real-world long-context tasks. In terms of probing tasks, the study introduced val probing, which included 3 tasks covering various context styles: document, code, and structured data context, and information retrieval patterns, forward, backward, and bidirectional retrieval. The results of the probing tasks demonstrated that Film 7b consistently exhibited robust performance across different positions within the whole context, overcoming the lost-in-the-middle problem that the vanilla Mistral model experienced. Additionally, the comparison between Film 7b and GPT-4 Turbo on val probing tasks showed that Film 7b achieved comparable performance with GPT-4 Turbo on the database probing task and exhibited better robustness in document and code probing tasks. In terms of real-world long-context tasks, the study evaluated Film 7b on 9 tasks from the long bench collection, including long document question answering, multi-document, multi-hop reasoning, and long context summarization tasks. The results showed that Film 7b significantly improved the performance of the backbone model in real-world long context scenarios and achieved state-of-the-art level performances among open-source models of similar size. Notably, the improvements in performance on real-world tasks indicated that the long-context capabilities learned from the synthesized data during IN2 training could be effectively applied to real-world scenarios. Furthermore, the study maintained that Film 7b did not compromise the performance on short-context tasks, confirming that the short-context capabilities of the model were retained during training.
What specific results were achieved with the application of IN2 training on FILM 7b, and how do these results compare to other models like GPT-4 Turbo?
With the application of IN2 training on FILM 7b, specific results were achieved in terms of significantly overcoming the lost-in-the-middle problem for the backbone model, as demonstrated in probing tasks encompassing various context styles and information retrieval patterns. Film 7b exhibited robust performance across different positions within the whole context, showcasing a substantial improvement in long context information awareness. Furthermore, Film 7b achieved comparable or even superior performance to GPT-4 Turbo on probing tasks, particularly excelling in document and code probing tasks, as evidenced by the average score and min-max gap metrics calculated on val probing. These results indicate that IN2 training effectively enhanced Film 7b's long context capabilities, enabling it to match or surpass the performance of proprietary models like GPT-4 Turbo in certain tasks, showcasing the potential for open-source models to close the performance gap with proprietary counterparts.
What are the limitations or potential drawbacks of the IN2 training approach for enhancing long-context LLMs, and how can these limitations impact the generalizability of the method in different contexts?
The limitations of the IN2 training approach for enhancing long-context LLMs include the potential bias introduced by the synthesized long-context data and the reliance on a specific training paradigm. The method may struggle to capture the full complexity and diversity of real-world data, as the training data is artificially constructed and may not fully represent the nuances of natural language. This limitation can impact the generalizability of the method in different contexts by potentially leading to overfitting on the synthesized data and underperformance when faced with real-world variability. Additionally, the IN2 training approach heavily relies on the instruction tuning paradigm, which may not always be feasible or optimal for all applications or scenarios. This reliance on a specific training paradigm could limit the adaptability of the method to different training setups or tasks that do not align well with the instruction tuning approach. Overall, these limitations could hinder the ability of the IN2 training approach to effectively generalize and perform well across a wide range of real-world contexts and tasks.